Good morning. Today we are standing outside the main doors to the machine shop, and what we see is a lot of information on the door. But the main thing that we need to focus on is the safety rules, and we have a set of safety rules on the way in before you go in, and I'll show you those right now and explain them. You can see pretty much everything, I guess. Okay, so the machine shop rules. Obviously no food and drink, no open-toed shoes. The type of shoes that you need to wear in the machine shop are safety shoes that have the green CSA patch. That's important. Eye protection, as I'm wearing safety glasses with side shields, mine are prescription. We have normally we have glasses available. I think that during COVID we would prefer that people had their own to use if they were in the shop, but there's not going to be any of that right this semester. But when time comes, that's what we will require is safety glasses with side shields. And anything like that, these are sufficient. We have a type of a goggle that goes over top of prescription glasses for those that wear eyewear to be able to see. Now, the rules, they're here to protect you. Access is only available during our open times for general use and using machinery. You must have a red or yellow training card. Now, a yellow card would be to operate machines like a drill press, hand tools, the saws. We have band saws. We have a wood band saw. We have a metal band saw. And I'll go over a little bit of safety regarding that as much as I can by video. We have obviously quite a few drill presses, so that's important. So a little bit of safety with that for sure to keep yourself from getting hurt. And okay, you must meet with the machinist before starting any work to make sure that you take the right type of material that is allotted for your particular course, and just to make sure that you're not doing something unsafe or you're planning to do something that could be dangerous. We can help a lot with that or direct you to a safer way. No food or drink or open-toed shoes allowed, as we've already shown with the pictures. Safety glasses to be worn at all times. Now, we don't want to see people wearing them on their head like this and then bring them down when they think they need them. You never know what someone else is doing that something could come flying across the room. You never know. So just to be safe, we should wear them all the time. Shop coats and gloves are available and recommended for general use. Keep your clothes clean. Our shop coats have short sleeves, so they enable you to handle things safely without your sleeve being caught in a drill press or a machine or anything like that. Obviously, long hair should be tied back while working on equipment, especially rotating equipment like a drill press. So make sure that your hair doesn't get caught in a machine or a drill. Long sleeves must be pulled up. Also, your sleeves can pull you into a machine. You need to make sure that your sleeves are pulled up, and once again, hands and arms are free from things that can catch on any type of machine. Horseplay, fooling around, we obviously can't tolerate that. It's a dangerous place, so very serious. But we enforce that. Do not operate any equipment without proper training and permission. Obviously, there are some machines that are off limits, such as the table saw, as it's something that the other machinist, Ken Graham, and myself, David Wright, we will do that and operate it for you. We have other machines that you can use, and if you're not sure of anything, how to use them, or if you feel unsafe, please speak with us. Normally in 2180 we do a complete tour and training for yellow card, we call it, and that would be, normally most things would have been covered, but perhaps something you're not sure of. We're always here. If you see anything unsafe or conditions that look unsafe, please notify us and let us know. We'll try and rectify it and make it known that there are no problems in the shop. Know the locations and operating procedures of all safety equipment, including first aid, fire extinguishers. Know where the fire alarm and exits are located. That we will definitely go through with people as they come into the shop for any type of yellow card training. And also, it's very important to clean up your work area when you're finished and put all the tools away. The next person that comes in shouldn't have to walk into an area that's covered with machine shavings and all of the tools are everywhere and not in their proper location, so that when they're looking for them, they can't find anything. That's very important. Okay? Thank you. Good morning. Today we are going to go over the metal lathe part of the 2180 Introduction to Manufacturing Processes course and explain the parts of the machine, some safety, obviously, and we'll go over what the machine can do. These are standard modern machines. They're quite versatile and resilient to student use. And you'll have a little bit of help when time comes that we're all back in the shop with my partner Ken Graham and myself, David Wright, as your instructors. So today we will go over the parts of the machines, how to select your speeds and your feed rate. In this view, you can see that we have a fairly long machine. This is the headstock. Contains all of the gears to set your RPMs. This is the chuck, it's the work holding device. This would be the saddle. We'll go over how to select your speeds in a few minutes. But this is your saddle with your cross slide. It would be your x-axis. Z-axis is towards and away from the chuck. And at the far end we have the tailstock, which will also slide and lock. You can extend and retract drills, live centers, different things that you'll learn about. But today, what we need to know is a little bit about safety. We need to make sure that everybody that comes into the shop is wearing safety shoes with the green CSA approved patch and safety glasses with side shields as well. Here we have our surface feet per minute and RPM chart. This is how we calculate the surface feet per minute and for the type of material that we're using. And from there we are able to calculate the RPMs to use. If you notice, it's a high-speed steel end mill chart that we generally use it for everything here. It's rather simple. If you remember, we're going to use a 2.5-inch diameter piece of aluminum to face on the lathe in our first operation. So what we need to do is find the material on the surface feet per minute chart. Aluminum is the very first one. we've roughed it off to approximately 600 surface feet per minute. We come down to the RPM chart, and we find 600 surface feet per minute right here, the diameter of 2.5 inches. It's 917 RPM. That is with a high-speed tool, like a drill or a center drill. Well, you may speed it up for a center drill because the circumference is quite a bit smaller with in the center, because it's not turning as fast as compared to the other 2.5 inch diameter. So that's okay with high-speed steels that are ground, or tool bits that are ground to shape. But most of our work is done with carbide tooling, preformed inserts, and in that case we would multiply this value by 4, so 36, probably about 3,650 RPM, somewhere around there. There's an exact measurement that would be closer, but that would be almost twice as fast as the machine can run. Now these values are calculated with perfect conditions in mind. Super sturdy machine, brand new inserts, coolant flooding on the part perhaps. That would be ideal. In our case, our machines are sufficient for what we do here. They're not the biggest machines in the world, or nor the most rigid, but they are very good. We backed off these values by about 30% at least, and you can never really go too slow. It's just it's good to have your tools last longer, and the vibration factor. You know, if the tool's hanging out too far, more than it needs to be, definitely there would be some vibration, and that would be a consideration as well. So bring it back about 30%. I would say, well, somewhere around maybe 2,000 is the top speed of the machine. I wouldn't even run at the top speed. I'd bring it back to the next lower speed, which would be about 1,400. Now that should be fine for this. If it were a piece of low carbon steel, we would estimate it to be a 75 surface feet per minute situation, and from there we go down to 2.5 inch, and we get somewhere around 115 RPM, which is a little bit slower. Multiply that by 4, you get about 460, and back it off 30%, maybe 300 RPM. I do believe we have some speeds close to that RPM, and that's pretty much it. Just about everything that you need to use or do. Aluminum, bronze, steel, low carbon, higher carbon steels, stainless, titanium, nickel, zinc castings. We have a way to find the proper speed for any of those. Thank you. Now that we have arrived at an RPM, this is the hit stock of the machine, once again, and this is the chart and the list of speeds that we have, the RPM selection. The top row, or 6 speeds, are in slow range, and to achieve these, if I want 40, which is the very first speed, as this drawing or depiction shows, the handle to the left, and that would be down, the second handle. So now we have this set at 40 RPM. 80, 160, okay? 350 would be up, as the drawing shows you. 700 here, and 1400 there. Actually 700. There. My apologies. Make sure that you always have the emergency stop engaged. Every machine has one of these emergency stop buttons, and let me show you that right here to turn it on. And anytime you're working with the chuck, changing speeds, doing anything like that, make sure this is off. Okay? Now, down below we have the high range, the fast range. In order to do that, same rules apply. You move it to the positions that you want for 57, 115, 230, and the same 500, 1000, 2000. However, in order to go from low range to high range, there is a knob at the, I guess it would be your left side of the machine. In this drawing, it shows to push and twist for slow range and pull and twist for fast range. Okay, the handle there talking about or drawing depicts is right here. So either we push and twist or pull and twist. So now the power is off. We've hit the switch. So safely should be able to change from low to high range. I placed the low-high handle that you saw in the middle area, which puts the machine in neutral. And I will spin the chuck by hand. And you may even see that from here. Okay? And the handle is pushed and twisted. You'll hear a click or pull and twist. And you will be in high range. So low range, push and twist. High range, pull and twist. And that covers how to select your speed. So now we are facing the chuck, the work holding device on an engine lathe. And in order to be able to clamp your material, we have a chuck key. Now ours, we have springs attached to them. That way someone can't leave the chuck key in the machine and turn it on and have it fly across the room. Once again, I have the power off right now to make sure that nothing can happen to me while I clamp this piece of aluminum. This is our 2.5-inch diameter piece of scrap aluminum that we're going to use as a demonstration on how to clamp it. I'll set it in, and if it's too small or too big, you have to adjust the chuck to that size. And once you get it in, we tighten it up. Make sure it's tight, and place the chuck key in this little containing tube that we have on each machine. Make sure that it doesn't get lost or fall in while it's running. And I have it set at 1400 RPM. So I have it up in low range and pointing towards our 1400 number on the chart. So that is your speed selection finished. Okay? The other parts of the machine are reasonably easy to demonstrate now. This is the tailstock. I'll move it out of the way, and we're going to show a little more here. Once again, this is the saddle, cross slide. So that's Z-axis, X-axis. We have a digital readout, and anytime you come in to use the machine, you press clear, and it actuates. You can change values, and so you'll enter and start over from there, and it will show a change as you move it. Also, the Z-axis. See, enter, and from there, you can use it that way. If we press the 0 button, it also says inch underneath. It will change from imperial to metric. So whichever you decide to use, you can. And that covers the digital readout. This unit on top is the compound rest. On top of the carriage, that is the compound rest. It can be swiveled to any degree, and you can use this compound rest handle to go in and out. It is completely independent from the readout, so when you use it, you'll have to recalibrate your X and Z settings. Okay? And lastly, we have the tailstock. The tailstock, as I showed before, moves quite freely on these bedways, the machine's bedways, which are hardened and ground to a precision fit. It moves really easy. We lock it with this handle, and the handle at the back will extend and retract the quill, the front section. We have a graduated quill with imperial measurement on top and metric on the bottom, depending on which you're more familiar with. To remove something, this is a live center. It's something that we may insert after a part has been center drilled. Just maybe getting a little ahead of us right now, but this is a center drill. It has a pilot and an angle that it will cut that's 120 degrees, or 60 degrees, my apologies, 60 degree included angle, and it fits this cone shape at the front of the live center, which spins and locates something that might be really long, and you may want to steady it as you machine it. It's the only way to do that. I would say it would be rather dangerous to machine something quite a bit out of the chuck without support, as this will give you. Now, to remove this live center, we'll bring this back, and out it comes. This is a Morse number 3 taper. It fits like a glove. As I brought it back, I won't be able to put it back in, so I move it forward slightly and put it in. Let's loosen the lock. You can see the suction power of that taper and how it holds it in. Okay, so once again, we'll take it out and set it back in our little spot to hold all of our tools. And moving forward, we will try adding a drill chuck to our tailstock assembly. So we bring that out once again. Otherwise, once you've retracted and taken something out, there's no way you can put something in. Just to save you a lot of aggravation in the future, that is why. It has a positive knockout. As you bring it back, the taper goes back, the screw pushes it out. So now what we've done is brought it ahead, pop in our drill chuck, and whenever you use a drill chuck, you will need to have a chuck key. Now, we like to have the chuck keys in this spot every time, but I had to go and search for this, unfortunately. To open and close the chuck, we use this chuck key and turn it to the right or left, whichever opens and closes it, depending on what you want to do. In this case, let's say we want to insert our center drill. I might move it by hand and then tighten it up. So I would bring that to the part. If it was running and we were closer to it, I'm going to move all of this out of the way, give it more room. and lock it, extend until I center drill it to the depth I desire. Bring it out, maybe take out the center drill and install a drill and drill a hole, whichever you might want to do. Okay? So I think that would be about as much as we can cover about speed selection, a little bit of safety, a lot of safety actually, and how to come up with the RPM and open and close the chuck to install the workpiece and drill a hole, let's say. In the next videos we'll move on to facing and turning operations on the lathe, and perhaps we'll go as far as some grooving, parting off, cutting something off, and hopefully we'll get a better understanding of how this machine works. Thank you. Here we have the turning tool as it sits in the clamped in the tool post. I'm going to demonstrate a little bit by using this pen that I have. The pen, let's say the pen represents the work, and the tool touching it, you can see that there's some angle. That's our relief. That's our side relief. We also have some on the front. If we were turning something, we can't have the whole tool scraping against the part. We only have the point. So there is some end relief as well. There's also a relief, it's kind of hard to show, I guess, from the side, that the point is the furthest out, a relief such as this at the side and at the front. This is the turning demonstration, parallel turning on the lathe with a large piece of 2.5-inch diameter aluminum. I have taken the liberty of center drilling and facing off this part, but I don't know if you can see it or not, but there's still some saw cuts on this part. I prefer that we remove all of those in the future, but I wanted to show you what they look like. This is about 60-70% faced, and that would mean that this area obviously isn't faced off. You could go a little bit more and finish it, and then everything that you make, your turning diameter would be axially square with the face of the part. That's always important. So what I'll do now is I will take out the drill chuck and steady this with a live center. And before we start cutting, I'll show you how to arrive at your speeds and feeds. Or your feeds, I mean, we know we have our speed set. So we always wipe off a taper, make sure there isn't any debris inside. Bring that out, pop it in. And I know that the last cut that I took is where the tool sits at this point. So I know that I need to come back to this point, maybe a little bit farther. So I won't bring this tailstock right up against it and not allow it to move anymore that way. I'll give myself a little space. Tighten it up and engage the live center. I'll quickly turn it on and show you how that works. It'll steady it as I remove material and exert force on it. It's less likely to come out and obviously hurt someone. Okay? So, from there, we will move around to our feed calculation chart on this lathe. Now, to set my feed, I have the chart here visible to set my feed rates, and what I've done is I've assumed that I will try to set this to be 11 thou per revolution for the facing operation. And so as I look at this, I see that I've already set it. I've found 11 thousandths of an inch per revolution right here. This pen, right there. So I have the pin set in number 5. You pull and slide it anywhere you want and bring it back up, and when it locks, it's there. And if I follow my 11 thousandths of an inch grid across, I get C and coarse. So C is here. It's that handle to adjust it. And coarse is once again back around. I think we covered this once before. Coarse is this handle on the back of the machine. Okay. This is where it is. Pull for coarse, push for fine. In our case, it's pull. Okay, now that we have our feed set, our parts ready to go, we are going to have our readout set up done. And so every time you come in, the power is on. It always returns to this mode. We hit the clear button. We know the front. The tool is already set at the front. So we'll call that Z0. Z0, enter. And we will take, I guess I will move it into imperial measurement. Now the diameter, we will need to obviously set that. But we don't really know where the tool is at this point, so I'm just going to double check it and make sure that this is 2.5 inches. It is 2.5 inches. So, assuming I need to take a lot of cuts and make a quite a bit smaller diameter, I will take a cut to find out where I am. Now to do that, I'm going to move the camera a little bit. Okay, so we'll turn on the spindle. Oh, I need to disengage the emergency stop. Oh, and also, I had it in neutral. I want you to see these things. So I'm set at 7 thousandths of an inch per revolution. And before I touch the part, I will let you see how quickly it moves. Okay? Now, to engage the feed, there's the red handle below by lifting it up. Okay? If you move it over and down, you will feed across the part. So make sure that you don't do that when you're parallel turning. We've seen people do it. Now, also, if we change the direction of the lead screw, which is this handle, everything would be opposite. When I engage this by lifting it up, it would move the other way, and it would face out if I were to bring it down. It would actually come towards me. But for what we want left-hand feed, and this will be fine for us. Okay, so now we're ready to turn. And what we're going to do is take a small cut, and I think I'll go in about 3 inches. And from there I will calculate, I'll show you how to set your diameter on the x-axis. Okay? So I'll bring it in until I touch. So I know I'm approximately 2.5 inches. I'll take a depth cut by looking at the diameter on the readout as it sits right now. It's 2.6. So I will move it in about 2 millimeters. And take the cut. These shavings are breaking off in nice little pieces. I've gone about 1.5 inches already, halfway. And I'm coming up on 3 inches now. So I'll stop it at about 2.9 and feed it the rest of the way by hand. And I am going to zero the x-axis at this point. Okay? So x 0, enter. Some people measure it now. They move the tailstock out of the way, and they bring it to that value they measure and zero it on the center line. I like to use my vernier calipers and measure the part. And you can't see me right now, but as I measure it, I get approximately 2.455. So how I will set this is I will bring it back. I will not have moved it, so I'll bring it back to where it was when I zeroed it at 2.455. It's a very sensitive readout. And it's X 2.455. Press enter. So now it's set on diameter at the size it is. Okay? So from there we can read the display and know where we are approximately. But I would always double check as you get close to your size, your finished size. If it's a precision fit, I'd be a little careful about using a vernier caliper. They're generally used for something between or within 0.005 of an inch or 1/10 of a millimeter either way, to be trusted for that. So we have better ways to measure fine diameters like micrometers. Ken and I use them ourselves quite a bit, and we'll probably help you with anything that you might need to do that's critical. Okay? So I'll take another cut. I think let's say we want to take this down to 2 3/8. 2.375. That isn't much more than a 2 millimeter cut. So let's bring it over here, and I'll move the tool. Actually, I'll back it off so that I don't rub against it as I go back. That could cause some damage to the tool bit. And I'll move it to 2 3/8, 2.375. Oh, darn, too far. Oh dear. Very difficult to get it exact sometimes, and quite often once the tool touches the workpiece, it changes again. I think that's close enough because I have a feeling it usually changes and goes bigger. So it might just pop it right into the perfect position. So here we go. Three-inch long cut at 2.375. And it actually bumped, you can't see it, but it bumped back to about 2.375 and 2/10. So we're pretty close. And we'll stop that in time. You'll have a difficult time trying to stop it on the exact lead position. And we are coming into here we are. So what I will do now is rather than, I'll show you what it looks like. If I don't move it back, see those little lines that are scraping against that? That's deflection. So always bring it back if it's important, and unless you have a lot of cuts, it's an extra step. You know where you are by the readout, so that should be fairly good for helping you have the tools and inserts last. Okay? So that is turning on the lathe, the turning demonstration. So I've increased the feed to 11 thousandths of an inch per revolution by adjusting it in the feed gearbox. So we'll see what happens now. I'll take a cut of about 2 millimeters. So that will be 50. My goodness. There. About 2 millimeter in depth. Turn it on and I'll engage the feed. In case you can't hear me, I'll tell you this now. There, 3 inches deep. You can see that the shavings came off in smaller pieces, much easier to manage than long stringy shavings. So that's 11 thousandths of an inch per revolution. You'll find proper calculations for every diameter of anything that you make, depending on the material. But in this case, you know that we're using a machine that can't achieve the speed that's recommended, so I'm working with it to show you how it would be when you come in the shop and use these machines. I have changed the settings to 3 thousandths of an inch per revolution in feed, and I've already set the X-axis for a 2 millimeter diameter cut. We'll see what happens with this one. I need to put it back in gear. I turned the power back on, but forgot to put it back in gear. There, that's enough. I don't need to go any farther to show you what would happen if your feed is just too slow. So try and keep that in mind, that you need to increase the feed if you see the shavings wrapping up like this, and try to come up with something that works. It doesn't need to be perfect, but that certainly is a lot safer this way.